Okay, thank you very well. Thank you very much for having me. My name's Harry. I'm a particle physicist. I'm going to talk to you tonight about the other end of the scale, so talking about the really smallest things in the universe. I'll just begin by introducing the instrument that I work on. So this is the thing that I spend my time studying the data that's produced by this thing. This is the Large Hadron Collider. It's the largest scientific instrument that's ever been built by the human race. By some measures, it's the biggest machine that's ever been built. It's a 27-kilometer circumference particle accelerator. This is an aerial shot taken from a plane of the area just outside Geneva, where it's based. It's actually on the border between France and Switzerland, so the protons have to go through border control several times as they go around the ring each time. And this machine really, I mean, in a way, particle physics is the most simple-minded, stupid kind of science you can imagine doing, which is really, we take things, we hit them into each other very hard, and we see what happens to try to figure out what they're made from. That's really more or less what we're doing. I'll talk more about exactly how this machine works a bit later on in the lecture. But the purpose of these kinds of accelerators is to understand the structure of matter at the shortest distances, the smallest scales that have ever been probed, and that's what this machine is for. So you can think of it in a way, it's a sort of gigantic microscope in some sense. Now, to begin the story, I'm going to take you back in time a little bit. So, well, first of all, I'll say this huge machine is run by an organization called CERN, which is the European Organization for Nuclear Research, which is a large international body, and it's based in Geneva. And this is a photograph of the CERN site. It's the size of a small town, except it's a town populated exclusively by particle physicists. So you can probably imagine what that must be like. And it has everything you would expect a town to have. It has restaurants, it has shops, it has travel agents, it has banks and hotels and so on for the physicists to stay in. But also somewhere on this site there is a large auditorium where the scientists present their results when they've made some new discovery. And this is the scene in that auditorium on the 4th of July 2012. So if you follow the news back in 2012, you couldn't have missed that a big discovery was announced at CERN. And that was discovery, well, what everyone in this room was cheering actually was this. They were cheering a bump in a graph. The physicists get very excited about bumps, but this was a very important bump because this bump told us that a particle known as the Higgs boson had been detected being created in the collisions at the Large Hadron Collider. So I'm going to tell you a bit later on about what exactly the Higgs boson is, but to understand sort of what it is, but also why we've got this big machine and the questions we're trying to answer, I'm first of all going to take you on a very, very brief tour of particle physics, beginning in the end of the 19th century. So particle physics is really the study, as I said, of what the universe is made from. And at the end of the 19th century, this is what we thought the universe was made from. So this is the periodic table of the chemical elements. There were about 90 or so chemical elements known at the time, and the view was that for each of these elements there was an atom, and these atoms were all distinct. So there was an atom for hydrogen, an atom for carbon, an atom for oxygen, and they were all different, and these atoms came together, they bound together to make chemical molecules and eventually to make living things like us. And of course, we now know this is not the end of the story. In the dying years of the 19th century, in 1897, at the Cavendish Laboratory, actually, where I work, a man called Joseph John Thomson discovered that you could actually chip little bits off atoms that are called electrons, and that began a process of understanding the deeper structure of the atom. And over the course of the first decade or so of the 20th century, the model of the atom was revised to this, which is the sort of familiar thing we all learn in school. So you have a central nucleus, which is positively charged and contains almost all the mass of the atom, and then around it you have these negatively charged particles called electrons. I'm just going to say I'm always very jealous of astronomers because you have beautiful images, and in particle physics we don't have any pictures of these things because they're too small to photograph, so I have to make do with crappy PowerPoint animations, so I apologize for that. Now this is the atom circa kind of 1913 or so. This actually, though, of course, isn't the end of the story either. In the 1920s and 30s, it's realized that the nucleus of the atom is not fundamental. That's also made of smaller things, and these smaller things are called protons and neutrons. These are subatomic particles, and there's two types, the proton, which is positively charged, and the neutron, which is electrically neutral. And the proton is particularly important because, well, first of all, the protons are the things that we smash into each other at the Large Hadron Collider, but it's also the number of protons in the nucleus that determines what an atom is. So a single proton, that's hydrogen, two protons, that's helium, and so on up through the periodic table. Now that is sort of, well, depending on how much physics you've done, that is probably maybe where you got at school, potentially. In the 1960s, though, it was realized this wasn't the end of the story either, and actually protons and neutrons themselves are made of even smaller particles, which are called quarks. And there are two types of quark in the universe ordinarily, the up quark and the down quark. The up quark is positively charged and the down quark is negatively charged, and these things bind together and they make protons and neutrons. So if you have two up quarks and a down quark, that's a proton, two down quarks and an up quark, that's a neutron. And that's it. So that's basically what we're made of. So these ideas came together in the 1970s and 80s to form a theory that we're still using today, known as the Standard Model, which is an incredibly boring name for one of the most exciting ideas that human beings have ever come up with. And the Standard Model is remarkable in the sense that it describes every object, or every sort of physical object that we've ever observed in the universe. It describes the composition and the forces that bind every structure that we've ever seen. And I use seen because you'll see why that's not completely true later in the talk. I'll take you very briefly through it. So the Standard Model, the first particle we found was the electron, and then the two quarks, the up quark and the down quark. And with just these three particles, you can make every atom in the periodic table. So you and I, everything in this room, we are just up quarks, down quarks, and electrons arranged in a variety of different interesting ways. That's it. Now, physics, for some reason, isn't quite as economical as this. So there actually are more than just these three. There's a fourth particle called the neutrino, which is a ghostly particle. They're kind of like phantoms. There are actually trillions of neutrinos passing through your body right now, every second. They're produced in huge quantities by the sun and in other astrophysical processes. We don't notice them, fortunately, because they have no electric charge. And the reason when we touch objects that they appear solid is because of the electrical forces between the atoms. These things which go straight through atoms, in fact, they can go straight through the Earth without interacting with the Earth. And they only very occasionally bump into things, so we're not really aware of them very much, which is good, because if they did bump into us, we'd be in trouble, because there's lots of them out there. Now, this column that we've now got, these four particles, make what we call the first generation of matter. And now, for reasons that we do not understand, for some reason, the universe, well, nature has provided us with additional copies of these four particles. So there's a second column in this table called the second generation, where all of the particles are replicated, but with larger masses. So, for example, the electron, the thing that goes around the outside of the atom, has a heavier version, 200 times more massive, called the muon, also negatively charged. It looks exactly the same as an electron, it's just heavier, and if you make a muon, it only lives for a very tiny fraction of a second before it decays into ordinary particles in the first column. So we know these things exist because they get created, first of all, they're discovered in cosmic rays, so particles coming from outer space, and people used instruments called cloud chambers, which allow you to see the tracks left by these particles. And they realized there were some other things coming down from space beyond just the ordinary stuff that we knew about on Earth. And now we make these things routinely in colliders. So with machines like the Large Hadron Collider, lots and lots of energy. That energy gets converted into matter, and when these particles come flying out, you see these things, these strange particles, muons, charm quarks, strange quarks. They all have peculiar names. And for other reasons we do not understand, there's a third column. So there's another column in this table, even heavier particles, even more unstable, they're even more short-lived. And we do not understand why we have these 12 particles. This is a mystery. In a way, it's a similar situation to the periodic table in the 19th century, where Mendeleev arranged the elements and he found that there were relationships in the way that they reacted, and these patterns seem to repeat through the table. We have something sort of similar here. The explanation for the periodic table is the structure of the atom and the way the electrons arrange themselves around the atom. We don't know what the explanation for this is yet. Perhaps it suggests some deeper structure, or perhaps it's something else. These 12 particles are what are known as the matter particles, so they sort of make up things that are the sort of solid stuff of the universe. But there are also particles associated with the forces that glue these particles together or allow them to bounce off each other or interact. And there are three different forces in the Standard Model. The most familiar is the electromagnetic force, which is the force that causes electricity, magnetism, and also light. Light is an electromagnetic phenomena. And the reason that you can see me is because there are lots and lots of particles called photons, which are the particle of the electromagnetic force bouncing off me and into your eyes, which are then interpreted by your brains. And so here we have the photon, which is the first force particle. There's also some particles called gluons, which are associated with the strong nuclear force. And this is a force that sticks the quarks together and the protons and neutrons together inside the atomic nucleus. And they're called gluons because they're sort of gluey. They stick things very, very, very strongly. And then there's some other weird particles called the W and the Z bosons. And these particles are associated with the third force, the weirdest of the three, known as the weak force. And this is a force that doesn't really stick things together in the way that, say, electromagnetism or the strong force does. Rather, the weak force is responsible for particles undergoing decay. So when an atom, for example, undergoes a radioactive process, that's often caused by the weak force. Or when a muon, for example, turns into a neutrino, that's caused by the weak force. So it's a force that allows us to change from one type of particle into another. Now, this was what the Standard Model looked like on the 3rd of July 2012, and then on the 4th of July we could add the final piece of this picture, which is this thing, the Higgs boson. So that's all of particle physics in about 5 minutes. I'll now tell you a bit about this Higgs thing and why we all got so excited about it. So first of all, to understand what the Higgs is, I need to say something about what a particle actually is. So the way I've described these things to you in the sort of animations I've used suggests that maybe these particles are like little Lego bricks or balls moving around in space. But that isn't actually what we think of particles as being at all. In fact, particles aren't really the fundamental ingredients of the universe. The fundamental ingredients of the universe are things called fields. So field is a sort of slightly abstract mathematical idea, but we've all encountered them. If you've ever held a magnet next to a piece of steel or iron and you felt a force exerted between these two objects, that's caused by a magnetic field acting across this empty gap, which allows a force to be transferred. Fields are all around us right now. There's an electromagnetic field in this room, which has got huge amounts of stuff going on. There's light, there's radio waves, there's microwaves bouncing around all over the place. So we're kind of familiar with the idea of fields. Now, it turns out actually that all these particles, for every particle in that table I just showed you, there is an associated field. So, for example, we have the electromagnetic field, the field of the electromagnetic force, and the photon, the particle of the electromagnetism is just a little ripple, a sort of disturbance moving through that field, which is all around us. And this is not just true for the photon, it's true for all the particles. So, for example, the electron, there is also a field associated with that. There's a field called the electron field, and electrons are just little ripples moving around in this electron field. You can think of it a bit like the sort of surface of a lake. The lake is like the field, and the particles are like ripples moving about on the surface. And there are quark fields. There's an up quark field and a down quark field, and so on. So every particle, there is a field, and all these particles are just little ripples moving around in these fields, which kind of is kind of an exciting idea in a way, because it sort of says that the atoms in our bodies are these slightly ethereal things, really. They're kind of disturbances in something much larger than ourselves. And in a way, all the particles in our bodies are connected to every other particle of the same type by this underlying field, which is always there. And this is a sort of silly cartoon that illustrates this point. This is from a mathematician colleague of mine at Cambridge, where this is particle physics at a collider, where you've got one particle here, a ripple in the field, another one, they're having a punch-up. So this might be a collision at the Large Hadron Collider, for example. Now, the Higgs boson, so what is this thing exactly? Well, when the Standard Model of particle physics was being put together in the 1960s, there was a deep theoretical problem that was come across, which was, it was known that particles have mass, because the objects we are made of have mass. So we knew this must be true, but it turned out that if you gave particles in the Standard Model a mass, the whole theory broke down. So you were unable to make any meaningful calculations with this theory. And Peter Higgs and a number of about 5 other physicists at more or less the same time, and I won't name them all because it would take too long, but they came up with an idea which was actually, well, maybe the particles we're made of really don't have any mass, but they are given mass by something. And maybe that way you can get out of this theoretical problem. And the ultimate solution was to say, well, let's imagine that the entire universe is filled with an invisible energy field. And this invisible energy field is what we call the Higgs field. Now, what happens is, say we take an electron. As an electron moves through this Higgs field, it interacts with the field, and the field kind of clusters around it, imbues some energy into the electron, and it acquires the property of mass through its interaction with this Higgs field. So in other words, the particles that we're made of actually don't have any mass, but they get it from the interaction with this invisible energy field. So that's the idea, and Peter Higgs wrote this down in a paper, and he sent it off. These are sort of the equations, this is what they look like. Don't worry, I'm not going to try and explain what they mean. But he sent this paper off to the journal, and it was rejected. And the journal referees wrote back and said, this is just some clever mathematics. It's got nothing whatsoever to do with physics and the real world. So Peter Higgs thought, well, okay, I've got to find a way of connecting this slightly weird idea with something that we can actually measure in an experiment. Now, as I said, the Higgs field, if it's there, it's invisible, we can't see it, but how do we know it's there? Well, in a way, it's a bit like the air in this room. We can't see the air in this room, but one of the ways that you know the air is there is you can hear sounds. You can hear my voice, which is a ripple moving through the air. And Higgs added one line to his paper to say, well, if this field exists, it should be possible if we can hit it hard enough to make it ripple, and that ripple will show up as a new particle, which is the Higgs boson. So the Higgs boson is really just a disturbance moving in the Higgs field. So the discovery of the Higgs proves that this Higgs field is really there. And that's why it was such an important discovery in 2012, because without this idea, the whole theoretical structure of which the Standard Model sits would just fall in on itself and nothing would make any sense. So it's lucky that it did turn up. Now, I'm just going to do a little bit, this is going to be a little bit of propaganda for why the Standard Model is great, so that you'll be really shocked when I tell you that it's also rubbish at the same time. So I'll just give you an example of the success of this, the power of this theoretical idea. So here's the electron, the particle that goes around the outside of the atom. Now, you can use the equations of the Standard Model to calculate properties of the electron to a very, very high level of precision. And one thing that you can calculate is the magnetic field created by the electron. So the electron behaves, it has an electric charge, but it also behaves a little bit like a little magnet with a north and a south pole. And you can use the Standard Model to work out how strong that magnetic field ought to be. And you can use a supercomputer and get a very, very accurate prediction. So here's a number to about 10 significant figures, 11596521807.3 times 10 to the minus 13. Very, very precise. And now if you do a very, very clever experiment at low temperatures and controlling lots of difficult systematic effects, you can measure the magnetic field of the electron. And this is the measurement. This is what you get. 11596521817.8. So these two numbers agree with each other to about 9 significant figures. This is the best scientific prediction anywhere in science, as far as I'm aware. There is no theory anywhere that can achieve this level of precision. So in some sense, this Standard Model that we're talking about is right. You don't accidentally get a result like this. It works. And in principle, this model should be able to describe all the physical stuff in the universe. The one big thing it is missing, though, is gravity, which is a pretty big omission. And that's one of the great goals of sort of fundamental physics, is to try to bring gravity together with a Standard Model. But other than that, if we forget about gravity, it does everything else. So it can tell us, for example, why these galaxies. This is a picture of the Abel cluster. I better be right on my astronomy because I'm not a bit sitting in the audience. But these are all. Each of the blobs in this image is a galaxy. Apart from you can see a few stars. These are the things with the little crosshairs. But you can use the Standard Model to, for example, to understand the nuclear reactions that are going on inside stars and why they shine. But we know that despite all the success of this theory, that it's at the very least incomplete and possibly wrong. And one of the reasons we know this is from astronomy. So this image, as I said, is of a cluster of galaxies. So what you can see in the middle here is a group of galaxies gravitationally bound together. And what you may hopefully be able to see, if it's not too faint, is that in this image there are these smeary circular lines. There's one just up here. There's a few more of them around here. You can see there's this kind of vague ring-like structure that seems to be going around this cluster of galaxies. Now what you can see in this image is something called gravitational lensing, which is an effect caused by the gravitational attraction of that cluster of galaxies bending light as it travels towards us through space. So if you can imagine that here, well, let's say that this is the Earth, and this is some distant galaxy, and then you have some very massive object in between you and that galaxy. As light travels through space, it's bent by the curvature of space-time caused by the mass of this very big object, and the light gets bent back towards you in a sort of lensing effect. And that's what you're seeing here in the sky. You're seeing the light being bent by the mass of this very large cluster of galaxies in the middle of the image. Now, Einstein's general theory of relativity is well understood, so you can use it to calculate how much bending you ought to get, how much of this lensing you should see, given the amount of visible material that you can see in this image. And if you compare how much mass there is in this image by counting the number of galaxies and sort of working out roughly how massive they are, and then looking at how much lensing you see, you find that they don't agree. And in fact, there's far more lensing, there's far more bending of light than you would expect from the amount of visible material in this image. And you can actually use it to map the distribution of the mass that must be there in order to explain why light is being bent in this way. And this is what this purple haze represents. This is something known as dark matter, which is some kind of gravitating stuff about which we know almost nothing. So one thing I should say, whenever you hear the word dark in physics, you should be very suspicious, because it basically means we don't know what we're talking about. So dark matter is just a word for some stuff, and we don't know what it is. There is no particle in the standard model that can tell us, that can account for dark matter. You can't combine quarks or electrons or any of the other things together to make something that has the properties that we need in order to explain dark matter. And the main reason is because dark matter is invisible. It's the reason it's called dark matter is because it doesn't emit, absorb, or reflect light. So we can't see it with our telescopes, but the only way we can see it is through its gravitational influence on the stuff that we can see. Now, from measurements like this, using lensing and lots of other measurements in astronomy, astronomers can come up with very, very accurate predictions, measurements really, of what the universe is made from. And this is our cosmic pie chart as it's currently understood. And this is based on the latest data from the Planck satellite. So 5% of the universe is made of atoms. That's us, and that's everything we see when we look at the night sky. So every star, galaxy, planet, everything is just 5% of the universe. So we are a sort of tiny little fraction of this total cosmic pie. 27% of the universe is made of dark matter, and we don't know what that is. And then 68% is made of something called dark energy, and we really don't know what that is. Dark energy, again, is another word for something that is some kind of repulsive force that's making the universe expand at an ever-increasing rate. It was discovered in the 1990s, and we haven't made very much progress in figuring out what on earth it is yet. And I'm not even going to talk about it in this talk because the LHC can't really help us there either. But one thing it may be able to help us with is this dark matter stuff. Okay, so that's one problem. The standard model, for all its success, is only telling us about 5% of the universe, which is a pretty big emission. Another problem with this theory is to do with something called antimatter. So the standard model, as I said, there are these 12 matter particles, the quarks, the electrons, and their friends. And we've known since the 1930s that every particle in this table has a kind of mirror image with exactly the same properties, but with the opposite electric charge. So you basically double the number of particles in this table, and these are called antiparticles or antimatter. So for example, the electron, which is negatively charged, has an anti-version called the positron, or the anti-electron, which is positively charged. The up quark has a partner called the anti-up quark, which is negatively charged instead of positively charged, and so on. And these particles, the antiparticles, are exactly identical to the ordinary matter particles that we're made of. The only difference is their electric charge, or their charges. That's the only difference between them. And one of the things that we notice when we do experiments is that whenever, say in a collider, if you're creating particles in some collision, you always make an equal number of antiparticles. So if you want, for example, to make an electron, you've also got to make a positron. And then if you bring those two things back together, they'll annihilate each other in a flash of light and turn back into gamma rays again, into ordinary light. So the point is, whenever you create or destroy a particle, you also create or destroy an antiparticle. And this is a really, really big problem, because if we go back to the very, very early beginning of the universe, so this is in a very tiny fraction of a second after the Big Bang, when the universe was still very small and very hot and very dense, you had so much energy go around at the time that the whole universe was constantly creating particles and antiparticles. You had electrons and anti-electrons and protons and antiprotons being created out of energy, annihilating with each other again and converting and so on. And then, as the universe expanded, it got to a point where it had cooled down below a temperature at which this process could continue. And matter and antimatter stops reacting with each other. And what should have happened, according to the standard model, is that because whenever you make a particle, you also make an antiparticle, you should have had an equal balance of matter and antimatter at this point. And then what should have happened is they should have met up with each other and completely annihilated each other, leaving you with a cold, dark, lifeless... why is this not working? Cold, dark, lifeless universe with nothing in it at all. So the Standard Model is telling us that the universe as we know it should not be here, that the matter that we're made of and that the stars are made of should not exist. It should all have been annihilated in some cosmic reaction with antimatter, a very, very tiny fraction of a second after the Big Bang. Of course, we know, in fact, the universe is full of stuff, which is really inconvenient if you're a theoretical physicist. You know, it would be much neater if there was nothing in the universe. That would be cleaner and simpler to understand. So, but unfortunately, there is a load of stuff, so we've got to somehow find a way of explaining this. Oh, hello. Spaceship there. Okay, so problem number one, we don't know what the universe is made from, really. Problem number two, the universe shouldn't be here at all. Problem number three, problem number three is actually to do with the Higgs boson, the Higgs field itself. Now, the Higgs field is unique amongst the fields in the Standard Model in that let's take the electromagnetic field. If you could go to a place, perhaps very deep in space, and put yourself inside a metal box, it would be possible to have a situation where there is no energy in the electromagnetic field. In other words, there are no photons moving around in the electromagnetic field. And at that point, the electromagnetic field has a value of roughly zero. Not quite zero because of quantum mechanics, meaning that you have these sort of fluctuations all the time, but more or less zero. The Higgs field is different. The Higgs field doesn't have a zero value. It has a constant finite value everywhere in space. So it's always on. It's always got some kind of, it's a bit like temperature. Rather than it being zero everywhere, it's always at, say, room temperature everywhere in the universe. And it's this property of the Higgs field that it's always got a value that allows it to give mass to the particles that we're made of. Now, this value, the value of the Higgs field, turns out to be an incredibly important number. Because if you change it, things get very nasty very quickly. And it turns out if you use if you use the theoretical machinery as we understand it, and try to calculate what the value of the Higgs field ought to be, you get one of two possible answers. So in a way, you discover that the Higgs field is actually a bit like a switch. It either it's either off or it's on, and there's no real kind of space in between that. Now, what does on correspond to? Well, the Higgs field being fully on means the Higgs field has an enormous value. In fact, it has a value up at something called the Planck scale, which is an energy way, 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 way beyond anything we can get in our colliders. It's the scale at which gravity becomes so powerful that it overwhelms the other forces of nature. And if the Higgs field had a value this high, then every particle in the universe would collapse into a black hole because its mass would be so enormous. So in universes where the Higgs field is on, you only have black holes and nothing else. So you don't have any atoms, and therefore you don't have any wobbly flesh-colored things made of atoms like us. So that's it. It's a pretty bleak place to live. The other alternative, the off position, isn't any better, really. If you have the Higgs field off, so it has a zero value, that means that the particles that make up atoms have no mass, and that means they can't bind together. So electrons never bind to atoms, and the universe is full of a kind of fuzzy static of charged particles zipping about, but with no structure in the universe. So again, in either situation, either you're all black holes or there's nothing because it's just this kind of dissociated mess of particles with no actual structures forming. Now, the value of the Higgs field that we have is just very, very, very slightly above zero. So it's not all the way up at the Planck scale, and it's not zero, it's just a tiny bit above zero. It's like the switch got stuck just before it turned fully off. And it turns out that if you move this number even a tiny bit, you very quickly find yourself living in a universe full of black holes or a universe full of static fuzz. And those two seem to be the only two possible scenarios. The only way to get a universe where the Higgs field has exactly this value that's necessary for there to be stuff in the universe, requires you to fine-tune the laws of physics in a really difficult to swallow kind of way. Now, to understand this, I'll use an analogy. So let's imagine that you're in a music studio, and there's a nice piece of music playing, and you've got a mixing desk in front of you. Now, these dials, let's say, for example, in the Standard Model of particle physics, there are about 25 or so different fundamental constants of nature. So these are things like the strengths of the different forces, the masses of the particles, and so on. And if you imagine these numbers are represented by these dials on the mixing desk, let's say you went up to the mixing desk and you turned one of the dials a bit, what would happen is that the music would stop playing. You'd be left with just static. And you could spend the age of the universe trying to discover where that dial was exactly positioned to get the music to start playing again, and you would never find it. So what this tells us is that the fundamental sort of makeup of the theory has been played around with to an unbelievable level of precision in order to get a Higgs field that has just the right value so that we can exist. Now, this is deeply troubling if you're a scientist, because this somehow suggests that someone has been dicking around with the universe to make it behave in a nice way, because this really shouldn't be how the universe ought to look at all. And this needs some explanation, and this is actually this third problem that really bothered physicists in the 1980s when it was first discovered, and it's motivated a lot of the big developments in theoretical physics and theoretical particle physics since then. And the best solution to this problem is an idea called supersymmetry. So supersymmetry is essentially it's a new type of symmetry. You can think of it as a bit like the symmetry between matter and antimatter, except this time it's a symmetry that relates the matter particles, so the things that make up our bodies like electrons and quarks, to the force particles, the things like photons. And in supersymmetry, every matter particle gets a force particle version, and every force particle gets a matter particle version. So you get a new table that doubles the standard model with a whole load of new particles, which again are the same as the standard model particles, except the matter particles and the force particles are switched around. And these things all have really stupid names. They're called sparticles. And if you want to know how to name a sparticle, you put an S on the front. So an electron has a force partner version called the selectron. The up quark has something called a sup squark. I think my least favorite is the strange squark. So yeah, anyway, physicists shouldn't be allowed to name things. There should be some kind of commission is the lesson from this. But it turns out that with this idea, with supersymmetry, this fiddling about you had to do with the laws of physics no longer applies. These particles cancel out, effectively, all these effects, and you're left with a value of the Higgs field at just the nice number that allows us to exist, and we don't have a problem to explain anymore. But now what this says is, well, if supersymmetry is right, there should be twice the number of particles that we've seen so far out there. And one of the big objectives of the Large Hadron Collider is to see if it can make these particles in the collisions and prove this idea right. Now, supersymmetry is great because it solves this fine-tuning problem, but it actually, one of the reasons people got very excited about supersymmetry is it actually solves a whole host of problems at the same time, one of which is to do with dark matter. So it turns out that in supersymmetry, the lightest sparticle and the most stable sparticle has exactly the right properties, usually, to explain dark matter. So the lightest sparticle tends to be electrically neutral and massive, which is what you want. So it can explain fine-tuning, but it could also potentially explain dark matter. Another very nice thing about supersymmetry, now this is a rather confusing graph, but essentially what you've got here, on the left-hand side, you have a plot of the strengths of the three forces in the standard model: electromagnetic force, weak force, and the strong force. And for some reason, strength is going down the way. So things down here are stronger, things up here are weaker. It's been known for quite a long time in particle physics that as you increase the energy of a process, if you collide particles in together harder and harder, the strengths of the forces change. And as you go up and up in energy, you see that these three lines, the strengths of the three forces, sort of start to come together. They don't quite meet, but they kind of start to converge. And this is perhaps suggestive that the three forces that we experience perhaps are just different aspects of some single unified force, which perhaps should be called the force. I don't know. Now, in the standard model, which is the left-hand plot, these lines don't quite meet. They sort of come close together at about 10 to 16 GeV. Don't worry really what that means, but they don't quite get there. If you add in supersymmetry, though, they meet rather precisely at a neat point. So supersymmetry appears to suggest the unification of the three forces into one, which again is a very nice thing. So that's another reason to like supersymmetry. Another reason to like supersymmetry is that there are now twice the number of fundamental particles to study, and that for people like me get kept in jobs for much longer period of time. So that's good as well. So we like supersymmetry very much. So as I said, the big objective of the LHC when it was built and designed and switched on was find the Higgs, job number one, and then find supersymmetry or find some other new physics that can help us to address the problems that I've outlined. So I'm going to zoom in now on Europe. I'm going to zoom in on the Large Hadron Collider and tell you a bit about this machine. So As I said, it's a 27-kilometer circumference ring. You can't actually see it on the surface because it would have annoyed a lot of farmers, so it's actually 100 meters underground in a tunnel. And what the LHC does is really kind of simple and quite brutal. At CERN, somewhere over here, there is a normal industrial bottle of hydrogen gas. The hydrogen is taken out the bottle, it's zapped with an electric field, which rips the electrons from the protons, which are the middles of the hydrogen atoms, and then it sends those protons round and round a series of accelerators. Eventually, they get into a machine called the super proton synchrotron, which in the 1980s was the most powerful particle accelerator in the world. It's now just a feeder for the Large Hadron Collider. So protons get injected into the LHC, one set of them going in a anti-clockwise direction and one going in a clockwise direction. And at 4 points around the ring, these beams of particles are collided. So every time these particles make an orbit of the machine, they are given a kick by a 2 million volt electric field, and they get accelerated to higher and higher energies, and eventually they are accelerated to 99.999991% of the speed of light. So more or less the speed of light, but not quite there, because we can't get there, unfortunately. And then they smack into each other inside these four big detectors. If you go down into the tunnel of the LHC, this is what you see, a very, very, very long blue tube curving away into the distance. What you're looking at here is essentially the world's largest thermos flask. This is a container, a highly insulating container, inside which are incredibly powerful superconducting magnets. And the reason that it's in this insulating container is because these superconducting magnets operate at a temperature of minus 271 degrees Celsius, about 1.7, 1.8 Kelvin, so just a smidge above absolute zero. And that is achieved by pumping liquid helium through the machine intravenously, which cools the magnets down to their operating temperature. And the reason these magnets have to be superconducting is because the protons are going so fast that they need an enormous force to bend them around the ring. And the reason the ring is so big is because we can't build, if we wanted to build a smaller accelerator, we need a bigger force to make them curve on a tighter path. That's why these machines are so huge. We're really limited by the strength that these magnets can get to. The LHC, the accelerator itself, is built by an incredibly talented team of engineers at CERN, and I have huge admiration for what they've done. And just to give you a sense of just one of the challenges involved in building this thing. So this whole machine is aligned to micron level precision. It's 27 kilometers in circumference, and as I said, it operates at minus 271 degrees. Now, I'm sure you know this, but if you get a piece of metal and you cool it down, what happens to it? It contracts, yes, it gets shorter. So this is a 27-kilometer long bit of metal that's been cooled down by 270 degrees. So it contracts by 30 meters when you cool it down to its operating temperature. And this whole accelerator has to flex and adapt to the fact that it's contracting under its own cooling without breaking anything, without misaligning. And the fact that it works at all is really, I think, quite miraculous. Now, at 4 points, as I said, around the ring, this tunnel opens up into these huge subterranean caverns. And this is a photo. I said we didn't have any nice photographs. Well, this is about as good as it gets in particle physics, the photographs of our instruments. So this is a photograph of one of the four detectors. It's called CMS, which stands for Compact Muon Solenoid. I always think it's a strange use of a word compact. Just to give you a sense of scale, this is a person standing next to this machine. So this thing is 15 meters high, it's 25 meters long, it weighs 12,000 tons, and it contains enough iron to make 2 Eiffel Towers. So it's a pretty big detector. You can see it here in this picture, it's been pulled open because they're doing some maintenance work on it. What happens is you can see actually here the beam pipes. This is the pipe that carries the protons. One load of protons come whizzing in from one side, this thing extends off the edge of the image, come in the other way, and in the middle of this detector, which is barrel-shaped, they crash into each other, and from their energy, new particles are created. And the job of this machine is to create very, very high-resolution, three-dimensional images of these particle showers that come flying out. And it has to do this 40 million times every second. It's a pretty impressive bit of engineering. This is one of the other detectors. This is called Atlas, which is even bigger than CMS. In fact, it's so big you can't really get a photograph of it because you're too close. When you go down to the cavern, you're just sort of doing this. You can't really get far enough back to get your shot. This thing is 25 meters wide and 45 meters long. They really are cathedral-sized, these machines. And this is what you get So when two protons crash into each other, this is what you see. This is a real image, well, a piece of data from CMS. It's a collision from about 8:30 in the morning on the 25th of June 2011. And what you can see here is two protons have come in, they've collided. And what happens when they collide is that new particles, new matter is created out of energy. You sometimes hear accelerators described as atom smashers, which kind of gives the idea that we're breaking atoms apart to see what's inside them. But that isn't what we're doing, really. We've known what atoms are made of for a very long time now. What the LHC really is a matter factory. It's manufacturing from energy particles that don't normally exist in the universe. And you can see in this particular collision, several hundred new particles have been created, and they go flying out from the collision point. And the job of the detector is to record the trajectories of all these different particles and to try to figure out what happened in the middle of this collision. So I'll just briefly try and explain that graph I showed you, that bump at the beginning. Now, one of the things we're looking for, as I said, is the Higgs boson. But the problem is that the Higgs boson only lives for 10 to the minus 24 seconds. So if you make one of these things, it lives for a trillionth of a second, and then it will decay into other particles. And it's so short-lived that it never actually hits any of the sensitive bits of the detector, so you never see it. All you see are the things that come flying out, the decay products of the Higgs. One of the ways the Higgs boson can decay is into two very high-energy photons, so two very high-energy particles of light. And this is what this image shows. You can see here, this is a cross-section through the ATLAS experiment. There's been a collision, and then these big yellow bars, they represent high-energy photons. And the job of physicists like me, data analysts like me, is to write algorithms that trawl through quadrillions and quadrillions of collisions in search of characteristic signatures like this. So if someone on the ATLAS experiment would say, I want to find the Higgs boson decaying into two photons, find me all the events where there were two high-energy photons produced. And what you then do is you add up the energy of photon number 1, the energy of photon number 2, and you plot it on a graph, and that's what you get. So what this graph is really just a bar chart. It's a histogram. And on this axis are the number of particles, the number of pairs of photons that you've seen. And on this axis is the total mass. So if you add those photons together, how much mass did the thing they came from have? That's really all we're doing here. And now, there are lots of ways to make photons in a collider. When you bang protons into each other, you get photons just produced at random. But what we want to know is, did these photons come from an actual Higgs boson? Now, the way you can tell is that the Higgs boson has a fixed mass. It always has the same mass. So photons that come from a Higgs boson will always add up to the same mass. And you'll see on this graph, the bump is where you've got a little excess of photons where their energies add up to the same number over and over again. And that tells you that there's a real particle, a new particle being created. Everything else in this graph is just background noise. It's just this tiny little wibble that's actually the evidence that the Higgs exists. And the thing that really got people excited on the 4th of July was, first of all, CMS showed their plot, and then ATLAS showed their plot. These two rival experiments on opposite edges of the ring both saw a bump in exactly the same place in energy. That told us that the Higgs really does exist. So that was, and everyone was rightly very excited about that and cheered and things. And yeah, it was kind of, I think it was one physicist in the room that day described it as being like a football match. There was so much sort of raucous cheering and shouting and things. I don't know if he'd ever actually been to a football match, but it was certainly quite lively by particle physics standards anyway. Right, so that's the Higgs. So that was job number 1, and that was achieved very successfully after about 3 years of taking data. And then everyone was sort of like, well, if we found the Higgs, so surely the sparticles are going to show up next, because supersymmetry says that if these sparticles fix the fine-tuning problem, they should have a mass about the same as the Higgs, so we should be able to find them quite quickly. But since 2012, it's really been a bit of a tale of woe. These are a number of headlines from sort of press around the world. This is a story from 2011 where some measurements actually made by the experiment that I work on had started to rule out a number of these supersymmetric theories. So LHC puts supersymmetry theory on the spot. Another one, LHC keeps bruising difficult to kill supersymmetry. Popular physics theory running out of hiding places. You sort of get the idea. And this is really the story of the LHC for the years since the Higgs boson was discovered. There was a little brief moment of hope. that came in about 2015. At a conference, the ATLAS experiment, one of these two big detectors, presented another graph with another suggestive little bump in it. And this bump was at about an energy 6 times higher than the Higgs boson, so it's much, much heavier if this was a real particle. And the problem was this bump wasn't yet at the statistical threshold to constitute really strong evidence, because just by random fluke, it could be that these data points had just fluctuated up a bit. But everyone got very, very excited, and this is a graph that shows the excitement of theoretical physicists as a result of this little hint of a bump. It's a number of papers submitted to the archive between the 15th of December, when the result was announced, and Christmas Day, the same month. And in that time, 100 papers were published or produced, trying to explain what this little wibble was, because there'd been such a dearth of new data since the Higgs. Everyone rightly got very excited about it. Unfortunately, it turned out to be rather premature, and when Atlas reanalyzed their data with larger statistics later in 2016, the little bump had just disappeared. And it turned out it was just one of these little random fluctuations. It wasn't a real effect. So that's a shame. So it really has been, if you're an experimental physicist, or indeed if you're a theoretical physicist, it's been quite a depressing time, if we're really honest, because we know we've got these great problems with the standard model, and yet nature is not telling us anything. It's giving us no clues as to how we might solve them. Now, there is, though, a bit of hope, a glimmer of hope, and it fortunately comes from an experiment in which I'm a member. So this is the LHCb experiment, which is another one of these 4 big particle detectors. It's not quite as sexy as ATLAS and CMS. It looks a bit like a kind of multicolored toaster or something, but it's a really great detector. And what we do at LHCb is slightly different to what ATLAS and CMS do. So these big detectors, ATLAS and CMS, they are essentially hunting for new particles being created. So there are 2 different approaches you can take in particle physics. So what ATLAS and CMS do is what we call direct searches for new physics. So it's the basic simple idea is you have one particle with energy E, you have another particle with energy E, you bang them into each other, and that means you can make a new particle with a maximum energy, a maximum mass rather, of 2e divided by the speed of light squared, because E equals mc squared, so m equals E over c squared, if you rearrange the equation. So that's all that is. So you basically, if you want to find, say, a dark matter particle, for example, you can only find dark matter particles that have a mass equal to the sum of the energies of the particles you're banging into. So if they were heavier than the LHC can get its protons up to, you're not going to be able to see it. So that's direct measurements. Now, there's another approach which is indirect, which is what LHCb does. Now, as an analogy, let's imagine that sort of ATLAS and CMS, they're a bit like hunters going out in the jungle looking for elephants. And what they've gone out with their gun, and they're wandering around in the jungle, and they're trying to find elephants. And that might be very difficult, because it might be a very big jungle, and there might not be very many elephants. What LHCb does instead is to look for the footprints left behind by the elephants. So even if there's only one elephant in the jungle, if it wanders about enough, it might leave footprints in lots of places. And if you find the footprints, you go, okay, well, I know there's an elephant in the jungle. I don't know necessarily what type of elephant it is, because I've only got its footprints, but that gives you a clue. And that's more or less what we do at LHCb. And the way this works is like this. So the B in LHCb stands for bottom, or beauty, depending on which you prefer. This refers to one of the 6 quarks. So the heaviest negatively charged quark is called the bottom quark. We tend to call it the beauty quark at LHCb because we'd rather be known as beauty physicists than bottom physicists. Anyway, these beauty quarks are very interesting because they're very heavy and they're very exotic. They can be sensitive to the existence of forces and particles outside the reach of our colliders. So to give you an example of this, so we produce lots and lots of these bottom particles, billions and billions and billions of them at the LHC, and these are unstable, they don't live for very long, and they decay. So let's say we start off with our bottom particle and it decays into some other bunch of particles. The way this would normally happen in the standard model is through the weak force, this force that's causing decay processes to happen. And we can use the standard model to calculate how often this decay should happen, because we understand the weak force in the standard model. Now, let's imagine, though, that there's another force, like a 5th force of nature that we haven't discovered so far. This force could also help this process along, so it can provide a different route from the initial state into the final state. And if this force exists, then it will slightly alter how often this process happens, or the rate at which this process happens. And so if you make very, very precise measurements of how often a bottom particle decays into some set of particles and compare it to the prediction made by the standard model, and if you see a difference, that is an indirect clue to the existence of some other force of nature that we haven't seen yet. So that's like the footprints, basically. That's what we're talking about here. So it's making precision measurements of ordinary particles that we know about already. Now, that's really mostly what LHCb does. It's what I do. It's what most of my colleagues do. There's about 800 of us or so. And we do lots and lots of these measurements. And then in 2014, one of these measurements came up with something rather interesting. So this particular measurement was, again, it's a decay of a bottom quark, decaying this time via the weak force into a strange quark, which is another type of quark, and two electrons, well, an electron and an anti-electron. Now, one of the rules of the standard model is a principle called lepton universality, which sounds rather scary, but all that really means is that the standard model treats the electron, the muon, which is the heavy version of the electron, and the tau, which is the even heavier version of the electron. There are three of these things. They all look like electrons. They're just more massive than each other. It treats these three different types of electrons exactly the same. So if we take another process where we exchange these electrons for muons, so instead we have a bottom particle decaying into a strange quark and two muons, then these two processes should have exactly the same rate. They should happen exactly as often, because the electrons and the muons are the same according to the weak force. It treats them identically. So a measurement was made by basically saying, let's find lots and lots of these decays where it goes into this bunch of particles and this bunch of particles, and let's compare them and see if they're equal, because they should be equal. And so what the standard model predicts is that if you take a ratio of the number of muon decays divided by the number of electron decays, that should be equal. So that gives you 1, a ratio of 1. And in 2014, this measurement was made where this value was measured at 0.75 plus or minus 0.1. So in other words, there was a shortage of muons. There were fewer muons being created than electrons, which doesn't make any sense because the standard model treats these two things exactly the same as each other. Unfortunately, again, this result is not yet precise enough to be able to say conclusively that you've seen anything. The 1 is the prediction. This is 0.75, so we're 25% away from 1, but our uncertainty is 10%. So that could just be a statistical fluke. So you need more data, you need more measurements. Another measurement was made in 2017. And this time, the number got even smaller, 0.68, and the error got a bit smaller. So it's getting further away from the standard model, and the error is getting smaller. So this is looking quite promising, and people really start to get excited at this point. And I think there are something like 500 papers on the archive now about this effect. And the really big news, this is more or less the first time this has been said, I think, like in a public talk at least, it's been announced at a conference, was we've just produced a new version of this measurement, and everyone was very, very excited. And I can now reveal to you the result. This is the result, 0.846 plus or minus 0.6. So what's really annoying about this is that the numbers move back towards 1, but the errors got smaller. So we're basically in the same place we were before, which is we don't know whether this is a real effect or not. It could be, I've spoken to a number of theorists about this, and most people are convinced this is not a statistical fluke. And the reason for this is that this effect is not the only one of its type. There are actually a number of different measurements of this sort of process that all have moved away from the standard model in a suggestive way that suggests there's possibly a single explanation, some kind of new physics explaining all these different effects. There is another possibility, which is that we cocked things up. There's some systematic effect that we missed, which could also explain these. So it's either we've made a big mistake, or we've discovered something really very exciting, which would be the first time we've discovered a new force of nature or a new particle for a very, very long time. But we don't know yet. So we're going to have to wait. This measurement was produced with data taken up until 2016, and there are 2 more years worth of data, 2017, 2018, that haven't yet been analyzed, which are much bigger in size. So we will know this year maybe, if we're lucky, or next certainly, whether this is a real effect. Now, what could this be? Well, I'll just finish with some speculative stuff, or at least this is what the theorists tell us. So these effects that we've seen, what they could actually be telling us is something, it's a question really that we've ignored in this talk, which is to do with the structure of the Standard Model itself. The fact that we've got these 6 quarks and 6 leptons. As I said, we don't know why that's true. It's this sort of weird periodic table, but we don't know where it comes from. It's possible that the explanation for this is something to do with where these different particles come from. So it's either something known as a leptoquark, which is a particle with the properties of both quarks and leptons at the same time, which would possibly be part of a much bigger theory. And that bigger theory would potentially explain where all of these different particles come from in terms of a single unified description, which would be really a very exciting thing. And this could be the first step on a journey to really rewriting our understanding of the basic building blocks of the universe. But we're going to have to wait a little bit to find out if that's right or not, or if it's just an embarrassing error. I'll just finish by saying, there's the LHC is actually shut down now. It's shut down until 2022, when it will restart again. So we'll have more data coming in the future. There is still some hope that, well, first of all, the big hope is that these effects turn out to be real effects and not some mistake. There's also still hope that we might find supersymmetry at the LHC, although most people have now more or less given up on supersymmetry, actually. So we're going to have to come up with some other ways out of this problem to do with the fine-tuning of the Higgs field and some other explanations for dark matter, because it's looking less and less likely that supersymmetry is the answer. And people are already thinking about, well, what happens after the LHC? The LHC's got about another 15 years or so to run. But at that point, it will really have reached the end of its useful life. And if we want to go out and keep discovering things about the universe, we're going to potentially need an even bigger machine. And this is already a proposal that's being seriously explored. In fact, it's being explored right now. There's a current strategy review going on this week to look at the future of particle physics. And one proposal is for an even bigger machine called the Future Circular Collider. Possibly should be called the Unaffordably Large Hadron Collider. And this would be a 100-kilometer circumference accelerator, which is the biggest one you can actually fit in the Geneva Basin, because if you get any bigger than that, you end up hitting the Alps, and that causes all kinds of problems with tunneling. So this machine potentially might be what we need. If at LHCb we confirm these discrepancies, it's quite likely that the particles that cause them, the elephants themselves, we'll have found the footprints, but to find the elephants, we're going to need a more powerful machine. So this may be the future of particle physics. Whether or not it gets built will depend very much in large part on whether these fluctuations turn out to be real or not. So it's a very, very exciting time to be a physicist. It's really kind of, as we said, I don't know if this translates very well, but it's squeaky bum time is what we say in Britain, but that means everyone's quite nervous and quite excited. If these effects are real, then it's going to be great. If they're not, well, we're going to have a serious rethink about how we tackle some of these big questions that I described in the talk. Well, thank you very much for your attention. Very happy to answer questions if there are any. Yeah. Yes. So, I mean, well, let's say these effects turn out to be real and we discover some new set of particles. It's quite like these particles, we believe, because of the symmetries between them, they fit into we're seeing some corner of a larger, more unified structure, in which there may be a whole bunch of other particles that we have never seen before, which could include dark matter. So we're kind of gradually, it's a bit like a jigsaw puzzle where we filled in a corner of the puzzle, and as we get towards the edges, we start to see hints of what might lie beyond it. So it could lead us to a bigger theory, which eventually gets at dark matter. I mean, there are lots of other ways, though, of getting it. There's colliders to try and make dark matter directly and see if you can observe it, but there are experiments that go underground with large vats of liquid gases where they wait for dark matter to bump into them. That's also searching for it. There are also astronomical observations where you look for dark matter annihilations in the center of galaxies, that kind of thing. So there's a broad spectrum of different sorts of experimental techniques being used to address these problems. We may be very unlucky, and if nature is just being mean to us, there's an assumption really about dark matter, which is that dark matter interacts through the weak force. We know it can't interact through the strong force or the electromagnetic force, because if it did, we'd have seen it already. And if it was electromagnetic, we could see it, and it would just be more ordinary matter. So it is allowed to interact with a weak force. That would give us a way of touching it. So it's possible, therefore, for dark matter to bump into atoms and for it to give off a signal, although very, very rarely, because it's only a weak process. But it's possible that dark matter doesn't interact with a weak force either, and then it's totally decoupled, and we'll never know what it is, probably. We'll just be able to look at its gravitational effects, and we might be able to, we can learn more and more about the kinds of structures it forms, I guess, by looking at, with greater and greater precision in astronomy, but we might never know actually what's the particle, or what is the thing that makes this stuff up. So it kind of depends on how nature is, really. Well, yeah.
I'm wondering if you can calculate the probability of finding a certain particle like the Higgs one. Otherwise, you have to wait. You have no idea, no indication how long you have to wait and to make experiments. Is there any probability measure?
Yeah, I mean, well, so the theory, for example, in the case of the Higgs boson, the theory of the Higgs boson was very, very well established before the Higgs was discovered. So we knew, the only thing we didn't know about the Higgs, we didn't know whether it existed or not, but the other thing, if it did exist, we didn't know its mass. But everything else we knew. So you could say, basically, you could precisely calculate how much data you would need to discover the Higgs if it had different mass values. So you kind of know basically how long you have to run your machines, how much data you have to take before you discover the thing. Now, that's true where you have a well-motivated theory like the Higgs, or like supersymmetry. Again, supersymmetry is written in the language of quantum field theory, which is a very well understood framework, and you can use that to make predictions of, if I have a certain type of supersymmetry, how often do I see squarks or leptons or whatever coming out of my detector? How long should I have to run my machine to discover them? But with stuff where you don't know what you're looking for, so there's the kind of, those what we call, I guess, known unknowns. So things where you know that they might be there, but you're not sure if they are. There's also things you didn't even think could be there, which you weren't expecting, and in that case, you don't really know. So you're sort of in the dark a little bit. But so we do, in most cases, you have well-motivated measurements. You know how much data you need. But there is also a type of investigation which is we just look and wait and see if we see something as well. Yeah, that's right, yeah.
And the neutron is like 2 down quarks and 1 up.
Yeah.
How does it work then? The proton is positive, but the neutron is like neutral.
Yeah. Yeah. So, well, the quarks have they have fractional charge. So the up quark has a charge of plus 2/3, and the down quark has a charge of minus 1/3. So if you have 2 up quarks, that's 4/3 minus 1/3, 1, and then 2/3 minus 1/3 minus 1/3, 0. Should have said that probably. You could have figured that out, I'm sure. Yeah.
So you said there's enough balance of matter and antimatter at that stage in the universe we are experiencing now. Is there any chance we are like in the matter corner of the universe and the other end might?
Should probably ask Professor Burkett that question. But I mean, yeah, as far as I know, and I'm not an astrophysicist, but as far as I know, if there were regions of the observable universe made of antimatter, then you would see at the boundary between a matter and antimatter region, you would see annihilations between particles and antiparticles. And that would give you quite a characteristic signature. You'd see photons with the mass of the electron, for example, maybe being produced. So you would, there would be, but it's possible, things, if there was like an isolated galaxy made of antimatter, there is no observation you can make of it that would tell you it was made of antimatter unless there was some matter nearby interacting with it, because the two forms of matter and antimatter, they're identical, exactly identical. So if you met the anti-version of yourself, before you shook hands, you wouldn't know that there was anything fishy, and then when you did shake hands, very bad things would happen. So, but as far as I know, the astrophysical evidence says that we cannot see any regions of the universe that appear to be made of antimatter that are in contact with regions made of matter, at least. So you kind of have to go on the assumption that the whole universe is made of matter, for now at least. Maybe beyond the edge of the cosmic horizon, there's some, the boundary beyond which we cannot see because the expansion of the universe is moving away from us faster than light. Maybe there's antimatter over there, but we don't know. So we kind of have to assume that the bit of the universe we live in is typical, and therefore there isn't any antimatter. Is that about right? Yeah, okay. Okay, well, thanks very much for your attention. Cheers.